So the previous 2 lecture weeks was about query optimization. Now we're going back to an application-oriented question, and that is in a domain of sub-problems of data management that are coined trading, banking, and ticket systems. And you will soon see what that is about. So we're back to this structure. So we have a concrete application. Then we will be looking at what are the data management and analysis issues behind that. Then we look at slides, notebooks, and make the transfer to the concrete application again. So we will be looking at trading, banking, and ticket systems. And as a motivation, this is a couple of screenshots. I'm not sure whether you can read that from there, but basically that happened in 2019. There was a couple of banking crashes. So the most prominent crash was from a German bank where customers weren't able to make money transfers like for 2 days. They had problems with their landlords, the rent couldn't be transferred, they got in legal trouble. And so the system of a bank, or of that particular bank, crashed. These things happen, that's okay. But the severe thing that happened was that they couldn't get the system back up again. They had a hard time getting the system back up. And once it was back up, again, it crashed again for whatever reason. Yeah? And one of those failures I heard about from one of the banks was actually that they didn't have a split in a staging system and a production system. So when you develop real software, you will have different types of system, the last system being the production system, and you want to avoid at all costs to make a change to your production system. Yeah? And what one of the banks did was they did a change in the production system without testing it first in their testing and staging systems, and then boom, crash, and they had a hard time to recover that. Yeah? And that not only happened for one bank, it happened for multiple banks. Yeah, and was pretty weird that these things still happen. Given what is available in computer science. So the reasons for these failures were probably very different. But as a computer scientist, you can ask some questions. So why do these outages take so long? So it's okay if it's a few minutes not available, but for a couple of days, I mean, really? Why does it sometimes take so long to get the systems back to a consistent state and resume normal operations? And by consistent state, I really mean, you want to make sure that whatever you had on your bank account before the crash is still the same afterwards. At least not less. If it's more, it's okay. You won't complain. Yeah? But you shouldn't lose any money due to the crash. Yeah? That would be great. Yeah? Why are there so many failures, and why are so many customers? Oops. So my iPad decided to do an update. I mean, it's magic, right? We're talking about software failures, and then these things happen. I mean, it's staged, of course, right? Yeah. So let's wait for the update to happen. So this was an update being performed on the production system rather than the staging system. It was a mistake by Apple, right? That's how you see. That was a demo for today. Don't have more demos for you. Okay. Right. Yeah, so why are so many customers affected? And given the investments, why don't these systems run more stably? I mean, if banks, they have money, yeah? Their money can't be the problem there, right? And when dealing with data, there are numerous possible and typical sources of error, and they have been known for decades. And the interesting thing is, I claim that all of these errors could have been fixed, could have been avoided in the first place. It's really, really, from a database person, hard to understand why these things happen anyway, yeah? Because the solutions are out there. And we will be talking about solutions. And part of the solution space, I'm not saying that it's going to fix all of these problems, but if you know what data management systems can do, you will understand how much you get for free. Yeah? So what is a database management system? So I have been avoiding this term for the entire lecture so far, because it's a bit hard to define. Yeah? So I've been talking about data engine, SQL processing engine, always trying to avoid this term. Now I'm introducing you to the term database management system, DBMS for short. And when I say that, I always mean, of course, that's a relational database system, RDBMS for short, but usually we say DBMS. Yeah? So they have been developed since the 1970s, By the way, is the mic okay or is it too loud? Feels a bit loud, right? It's okay? Okay. So they have been developed since the early 70s and have typically the following features. So it depends on the product, but the most advanced systems have all of this. So they have an extended relational model. It's not just atomic attribute values, but it's JSON, XML, arrays, text, spatial data, you name it. All kinds of data, you can put it into your relations. They have a very evolved and extensive SQL dialect. We just scratched the surface. We had super simple queries in this lecture. I mean, the SQL standard defining what the SQL language can do is like 1 meter of books in a cupboard. Yeah, it's insane what you can do with SQL. Huh? They have an automatic query optimizer. We looked at that. Yeah? We only touched the surface. So these query optimizers make a huge difference in practice. Yeah? If your query optimizer solves the problem of a customer, well, then you're in business. If it does not, maybe you're not out of business. Yeah? So these companies developing these systems invest a lot of money to getting the query optimizers right to make their customers happy. Yeah? It's a huge effort, and there's a lot of research that can be done there. Yeah, these systems are very high performance. Again, this depends a lot on the query optimizer and some other design decisions, but most of them are really super, super fast. There's massive support for physical design. By physical design, I mean that there's index structures, that's our term for data structures. There's tools available allowing you to make decisions on where to put data, on which machine should the data be placed, how should the data be stored, how many replicas do you create, how does distributed query optimization and processing work, stuff like that. So it's insane what you can do. And there's support for modern hardware. So modern hardware, you will read that in news articles very often. What is modern? Yeah? Modern with respect to what? Yeah? So modern these days is probably something like persistent RAM. Yeah, but I mean, back in the 90s, people developed database systems for hard disks. Yeah? So PostgreSQL, for instance, was developed for that. And then times changed. You could put all of your data into DRAM all of a sudden, and then you made different design decisions. So many modern database systems are actually developed for main memory or beyond, something beyond like PRAM, FPGAs, or GPUs. So many things are going on in that domain. And yeah, if you come to avoiding and dealing with error situations, as this week and next week, there are other interesting features database systems support. So there's extensive support for transactions and asset. What that is, I will explain in a moment. There's concurrency control, automatic concurrency control, meaning if you ever worried about that you have to create a thread here and then a lock and a mutex there, you can put all of that into the trash. The database system will handle all of that automatically for you. You don't have to know anything about concurrent programming. The database system will handle that, and that's awesome. There's automatic crash recovery, replication, and backup, meaning if you configure and use your system well, and the system crashes for whatever reason, it can happen, just a power failure, whatever, hardware failure, whatever, yeah, you restart the system and it will automatically reconstruct a consistent state. You don't have to do anything. It will recover automatically. It's like, I don't know, you have a wound, you bleed, and your body will heal that wound. It's the same thing for databases. It will heal your skin. You don't have to do anything. There's automatic consistency control. Yes, you want to make sure that you don't lose money, you don't give too much money to your customers after a crash, and the customers don't lose money. You can do all of that automatically. Often it's not used, unfortunately, but it's there. Then there's dynamic views and access rights, which is called, that is basically what we call logical data independence. That's not so important for the moment. We will focus on the other things. And what I actually promised when we advertised this lecture in the semester kickoff, there was this slide, if you remember. Yeah, I had a lot of bullet points on that slide. Yeah, I created a multi-user web application. He used ER, also entity relationship modeling, relational algebra, SQL. So ACID and ORM are still missing. We didn't talk about ACID and ORM yet. We will be talking about ACID in the next 2 weeks. And afterwards, we will also mention what ORM is, because these are super important tools allowing you to do these things. And that also explains the weird numbering. If you noticed here, it's not ABCD, but this is alluding to what is called ACID in databases. Okay, the analogy I will be using is this car. I'm not sure whether some of you know this car. That is the A-Klasse, A-Class in German. That's a car from the 90s produced by Mercedes-Benz. And basically what they did is they do all kinds of testing, whether the brakes work well and stuff like that. And shortly before, was it before production or even it was already sold? I don't remember, but it was already designed, everything was finished, everything was done. And then they did a famous test that's called the Elch test or Elk test. The idea is, all these cars are tested in Scandinavia because there's no traffic jam there, probably, whatever. And you're going to get all kinds of weather situations. So the test is you drive the car and then you assume there's an elk crossing the street in front of you. And then you have to brake like crazy to not hit the elk, to not hurt yourself and also not hurt the elk. Yeah, and they found out that for this particular car, the car was toppling, yeah, and it was falling to the left side or right side or making a somersault, I don't know. Well, it was pretty bad. They found out, oh, you can't really control that car in that situation. Yeah, that's what happened. So, this is the typical steering you have here, like a clutch, brake, and I don't know, gas, or what the name in German it's the type is, Throttle, okay, thanks a lot, yeah. So this is brake, right, and this is clutch, right? Okay, all right, yeah. And so what I found out when testing and finding that situation was basically, okay, actually what the user should have, the user could fix the situation easily. We just have to add the have to change the interface. That is part of the interface you have in the car. Yeah, those 3 pedals. So changing the interface would be something like that. You would say, okay, I have one brake pedal for each of the wheels. Yeah. If you have that, you can actually handle the situation with the elk easily. You just have to hit the right brake pedals. Yeah? Then everything is fine. Yeah? And that's the analogy to concurrent programming, of course. Yeah. If you understand concurrent programming, yeah, everything is good, cool, go for it, fantastic. But most laymen, and I also know many computer scientists who just, it's overwhelmingly complex. Yeah. So of course, you couldn't do that. Yeah. The typical car driver wouldn't be able to handle that. Even, I don't know, race drivers would be able to handle that. So what they did is they actually kept the interface. Yeah, so this is before 1997. There would have been the manual controls preventing the problem. They said, no, we can't change that anyway. So what we do is we add some computational power to that. Yeah, that's what was called electronic stability program. So say added computers to the car, analyzing the situation, and the computer would be able to remove some brake power or add some brake power on each and every wheel. And with that, you could avoid that the car would topple, yeah, and get in a difficult situation and hurt the drivers. And it was fantastic, yeah? Fantastic. And it was basically a workaround, yeah? Because the car was out, they had to sell it, so they developed that workaround. Yeah? But this stuff worked so well that it actually became mandatory in all new cars since 2014. Yeah? So if you bought your new car afterwards, you will have it, and it's awesome, yeah? Because it will help you in all kinds of weird situations. And you don't even notice this stuff. The computer will handle it for you. Yeah. Right. Questions? Yeah. There are many of these database systems out there. There's actually a database of databases. That's this one. Check it out. DBDB.io. If you have, so as of a couple of days ago, there are 904 database management systems listed there. Commercially, the most prominent are Oracle. Then there's Microsoft, SQL Server, IBM DB2, Action Vector, SAP has its own database. Exasol is not so widely known. I'm listing it here because it's from Germany. It's a German database company from Nuremberg. And they have been leading an important benchmark for like 10 years or so. And they're really doing a great system here. Yeah, in the open source domain, there's Postgres, of course, we use that, MySQL, SQLite, now there's also DuckDB, we use that in some of the notebooks in our own system, Mutable, but still research in the research domain, of course. Yeah, could you stop talking? Yeah. So the approach in the lecture so far has been, we didn't really use those fancy features of the database system. I mean, we basically used Jupyter notebooks. Yeah? So we had CSV files. We loaded them once into relations, into representations in Python, yeah, using DuckDB, for instance, and everything was single thread. Yeah? And then any number of read queries were issued on the relations. And yeah, if you only have threads or queries reading stuff, you can't have concurrency problems by definition. The concurrency problems can only occur if at least one is changing some stuff and the others are reading. Then you may be in trouble. But if everybody is only reading, it's actually easy. You don't have to worry about concurrency control. And that's what we did so far. Yeah. In particular, in single thread, also no problem. But if you have multiple threads, and at least one of the threads is changing stuff, then you have to be careful. Yeah? Yeah, now we are changing to a world where queries shall be allowed to change tuples in relations concurrently in any way they want. And in any way they want, we can look at that in a bit more detail. So the problem scenario is as follows. Yeah? It's really simple. I assume it's a bank and their customers that want to do something with their money in the bank, and the bank simply just keeps one relation. So this accounts relation, which has like the account number, or number for short, which is the key, yeah, and then that's the current balance. So your account in the bank is just one tuple in some accounts relation. So the scenario is we have multiple customers, they want to access their accounts at the same time. At least one customer changes his or her account balance by withdrawing, depositing, or transferring. Yeah? And now let's take a look at the different scenarios or problems that may occur in such a scenario. So, withdraw some money and deposit. That is not a problem if at any time a maximum of one customer accesses the accounts relation. So, basically what you're saying is, at any time, only one of the customers is served. Yeah? So assume you go to Mensa, and to avoid conflicts for people grabbing forks and knives and stuff, you say, oh, no, we fix that, that students get into their waste by just allowing one student at Mensa at all times. Yeah? You give some food to the student, yeah? Then the student walks to the table yeah? And eats the food. And then once the student is done, he leaves the Mensa, and then the next student can enter Mensa. This is not that efficient, obviously. Yeah? You don't want to do that, but that is the analogy we're talking about. Yeah? So basically, you lock the entire table, or you block the entire table. You only allow one customer at a time. Right. You could also do that per account. Yeah? You could say, okay, at any time, a maximum of one customer accesses a tuple of the relation accounts. So a tuple, yeah, before we had the entire account, but if you make sure, okay, every customer just works with his or her own tuple, everything is fine. Yeah, that's okay. The analogy for the Mensa would be, I don't know, you have one table per student, or one chair per student with a name. Only that student is allowed to sit on that chair. That is okay. Yeah? You must not sit on any other different chair where there's not your name tag fixed on that chair. That would be the equivalent. And of course, in terms of efficiency, it's kind of stupid because only when you are in Mensa, that chair will be used. Yeah? You won't reuse the chair for other students. Yeah? If you take like 30 minutes to eat and the Mensa is open like for 4 or 5 hours, yeah, only 30 minutes of the 4 or 5 hours the chair will be used. But it's okay. If everyone sticks to that model, you definitely increase the efficiency over just allowing one student to Mensa. Yeah? Conceptually, here the customer owns his account, or the student owns the chair in Mensa. Yeah? Yeah, but then it starts getting messy once you want to transfer money from one account to another account. Huh? So something like this here, you transfer 100 euros from whatever account 2 to account 7. So that is again okay if at any time a maximum of one customer accesses different tuples of the relation accounts. Yeah? So you must block access to all affected tuples of the transfer for other clients. So these two tuples at any time may only be accessed by this one customer. Yeah? The other tuples are not affected, but you have to block everybody else on those two tuples. Yeah? Then it would still work if you did that. Here we have two transfers. Here one from account 2 to 7, and then another one from account 7 to 4. Yeah? And then it gets really messy. Here again, you can block all tuples for each transfer. So block access to all tuples of the transfer for other customers. So what it boils down is you have to make a decision on whether you first do this transfer and then you do this transfer. Yeah, but if you kind of mess it up and mix the two transfers, you might end up with an inconsistent state and may lose money or add money artificially to the customer relations. Then this is another situation. So here you're transferring at the same time from this account 2 to 7 and from 7 to 2. Yes. So what do you do in this kind of situation? Well, how do you make sure that the state is preserved in your bank? Yeah? So we will be looking at these scenarios more formally and in more detail in the following. So what are the data management and analysis issues behind that? So how do we allow concurrent modification of data without creating erroneous data and without manually synchronizing threads? How do we design this so that the process and the resulting overall system are efficient? Yeah? You can easily fix concurrency control, make everything serial, just run everything in one thread. That's fine. Maybe that saves your problem, but typically you want to allow for concurrent users, concurrent threads, concurrent access, yeah, to make the system more efficient. So how do we do that efficiently and at the same time correctly? So we have a huge agenda for this week and next week, and it's a little bit more demanding topic than query optimization, I would say. So we will be looking at some of the highlights here. So one is, so we looked at database systems, the definition of what that is. Now we will be looking at the basic terminology like transactions and asset, and then we'll dive a little bit into serializability theory, just a little bit to get a basic understanding of what's going on. And then we look at concurrency control. So concurrency control is a component in a database system that guarantees this stuff, that guarantees that multiple threads don't destroy each other's data and everything is correct and efficient and stuff like that. And there are many, many approaches for that. We will be looking here at an approach that's based on locking, in particular two-phase locking. And there are other approaches. For instance, Postgres uses this approach that's used on versioning. That's more a topic for the core lecture database system. But basically, those are the two classes. So this is also called a pessimistic approach. So if things can go wrong, they will go wrong. And this is on an optimistic approach. No, things won't go wrong. I am optimistic, everything will be fine. But still, I will check whether things are okay. So we need a couple of definitions. So one is read operations and write operations. So what is a read operation? A read operation reads at most one tuple from one relation. And I will now define the granularity of reading. Because at most one tuple means in the following, it may mean that I'm only reading some of the attributes of the tuple, not all of them. Typically, I only read one attribute value of any given tuple. But important to understand is I'm not reading data from multiple tuples. It's only one tuple. That's important for the moment. Later on, I will drop that, but for the moment, it's really important. So this is the notation. And again, you will find that in the literature, like in the Kemper book, they use the same notation if you want to read it there. So here, the data object A, like the attribute values of a tuple, or at most the entire tuple, is read. That is the notation. Then there's a write operation, again in three different flavors. So we have insert, update, and delete. It also changes at most one tuple in a relation. Typically, only one attribute value is changed. But you have an insert, inserts a new tuple, you have update, changes one, several, or all attribute values of an existing tuple, and delete removes an existing tuple from a relation. And the notation is WA, write, write operation on data object A. Okay, so we have reads and we have writes. Yeah, what is the relationship to SQL? I'm introducing this notation because I want to get rid of writing all these long SQL statements. Yeah? So in SQL, this read operation typically corresponds to something like that. Yeah? So you have an access to a table foo using its key column. So I'm assuming ID is a key column, and then you have a where clause where you specify that key. And with a condition like that, you can get at most one tuple from the relation, yeah? Because the ID is unique, so the tuple with ID 42, it's only one tuple. So if that tuple exists, you get one tuple, otherwise you don't get any tuple. Yeah? So I'm accessing a single tuple. And rather than writing all of this SQL, I just write this one. And the same for this write operation. Rather than writing an update statement or an insert statement or a delete statement, I just write this shorthand notation, write data object A. Okay, so much about that. Yeah, with that we get to the term transaction. So what is a transaction? The transaction T bundles one or more read and write operations into an inseparable unit. The transaction defines the conceptual order in which its read and write operations are to be performed. And maybe we start with the example again. And then I first have to introduce this notation. So the beginning of a transaction is marked with a B for begin, the successful end with a C for commit. So in the example, you have it here, you have a B and a C. Then you have this subscript number that is just the number of the transaction. Yeah? So we will be looking at these. So this down here is called a schedule. Yeah? So we look at schedules where there are multiple transactions and they're interacting, and for that you need the number of the transaction where this operation belongs. Yeah, then we have these arrow notations saying, okay, operation X takes place before operation Y. Yeah? So whatever is this operation is executed before this operation. Each operation must take place after the begin and before the commit or abort. So basically this begin and commit are like brackets. Yeah? All the action happens in between those brackets, but not after the commit. After the commit, you are not allowed to do anything, and without a begin, you're not allowed to do anything. So here's a money transfer in that world. So that's what we saw before in the example. We have a money transfer from account 2 to account 7, as shown on the slide above. So K2, let's assume that that is a data object with a balance of account 2, and K7 is the account balance of account 7. So what you do is you read the old value, then you write the new value of K2. Yeah? You read the old value of K7, and you write the new value of K7. That is what the transaction defines. Notice that I didn't write down what I'm doing operationally. I never wrote that this value I'm writing here is, I don't know how much money we transferred, but assume I'm transferring $100 from K2 to K7. That means, of course, if I read the old account balance here, I must write old minus 100. Yeah? And if I read the old value of the target account, I must write K7 plus 100, of course. But that's not written down in this schedule here because the database system doesn't see that. So the database systems view is just seeing the read and write operations, but recall that basically, I mean, if you go back to this slide, as a user of the database system, you will be sending those update operations. And the database system only sees a new value, but it doesn't see the difference you apply to that. It sees, okay, there's a new value, whatever, right? Yeah, but the database system doesn't know how you compute the new value. So that's not denoted in those schedules. So. Yeah, so there's this host programming language, so be it Python, be it C++, where you write your SQL statements and then send them to the database system executes them. However, what happens in your host programming language is not known to the database system. The database system will only see the SQL statements, not the code in between those SQL statements in your host programming language. So that's very important. So we will assume in the following that we only see the read and write operations, so the same information the database system sees. And important for us is that with that information alone, we must be able to decide whether certain read or write operations could be problematic or not. Yeah? So we don't know what the host programming language does. Just based on this sequence of SQL operations we receive in the database system, we have to decide, yeah, that's cool, we will allow that, or you say, no, that's messing up the database state. We must not allow that. Yeah? That is a job of the database system. Yeah, so it's a little bit more formal. I don't know whether that helps you in any way. Yeah, the one thing we are introducing here, so we have this begin, we have a couple of operations on data objects, yeah, and so forth. And then to terminate the transaction, I so far introduced that there's a C for commit, but you can also say abort. Yeah, that's the A. Abort meaning, I sent a couple of SQL commands, but actually, no, I changed my mind. I don't want to execute those statements. That's what you're allowed to do. Yeah? You can always say at the end of the transaction, no, I don't want to execute that. Yeah? Then you say abort, and that's supported in SQL. Other than that, the slide is just a formal definition of what we had before. Yeah, one notation we need is the state of the instance and sequential and concurrent execution. So when there's a transaction Ti that is executed on a relation R and it commits, and you can do the same thing if that transaction operates on multiple relations, yeah, I'm just simplifying it to work on one relation, then we denote the state of the instance after executing the transaction with R, yeah, in brackets, squirrely brackets, Ti, yeah, meaning that is the state of relation R after the changes specified in transaction Ti have been applied. Yeah, so whatever you specified in your transaction as changes, updates, insert, delete, whatever, after you apply them to relation R, that is the new version, if you want, of relation R, yeah, the new state. And then you can differentiate sequential execution and concurrent execution. So in sequential execution of two transactions, we write it like this. Yeah? So first T1 is executed and then T2. First T1, T2. T2 is executed before T2. T1 is executed before T2, that's what I meant. Whereas in concurrent execution, we use this double pipe symbol, meaning there's somehow, T1 and T2 are somehow executed concurrently. I'm not saying how at that point in time, just saying they're executed concurrently. And after both of these transactions have been executed concurrently, I have a new state. And that is what this entire notation means. Yeah? After executing T1 and T2 concurrently, the new state of R is this one. Okay. Yeah, and with that we enter ACID. The abbreviation, each of these letters in ACID defines a certain property that must be fulfilled for transactions. And the first property is atomicity, Atomarität in German, capital A. So A means a transaction is an inseparable unit. The read and write operations of a transaction are either executed completely or not at all. So that means all or nothing. Whatever you specify in something like that, either all of the stuff is executed or none of it, not half of it. You know? So therefore, the state of the database after the execution of T is either whatever the state was before executing the transaction or whatever the state is after executing the entire transaction, but not half of it. Yeah? The entire, all or nothing, yeah? So nothing or all, yeah? In that notation. So for example, if you go back to the money transfer, 100 euro from account 2 to account 7, that was the transaction we listed above. So all of these actions are executed. And so if this commits, yeah, so you have a commit symbol and it's executed on the database like that, so all of these actions are executed, everything is fine. Atomicity is preserved. However, if you only execute it partially, yeah, like here, yeah, so what's missing here is this write operation, the writing the new state of K7 to the database is missing here, so that's not there. Here you say, oh no, I changed my mind, I do an abort. So here you need to ensure that the partial changes made by this operation. So here you changed something. You deducted the 100 euros, but you didn't add the, so you deducted 100 euros from K2, but you didn't add the 100 euros to K7. Yeah, so the bank wins. Yeah, that's maybe a reason for always execute it in this order. Yeah, maybe you could also say, I first give the 100 euros to K7, and then I remove it from K2, and if your system fails in the sense that it will partially execute transactions, yeah, here and there the customer will win. Yeah? But in this world we're in, it doesn't matter. It doesn't matter because the database system will only create them all or nothing, so it doesn't matter how you specify stuff here, whether you first do this and then you do this, it doesn't matter, yeah? Because it's all or nothing. Yeah? No, the bank cannot win and the customer cannot win. The bank always wins anyway, but not here. So this is a technique to make sure that the bank doesn't win. So this really implies that there's no half-hearted transactions. Yeah? So we must make sure that the database is protected against only parts of changes being executed on the database. And that sounds a bit like magic, but I will explain how that works. There are many things, many ways how to do that. Just for completeness, we will look at a different letter and asset, that's the I. Don't confuse that. Huh? So atomicity describes the behavior within an individual transaction, but shortly we will be looking at isolation, which describes the behavior among one or more transactions. Yeah? Maybe you can, once we introduced isolation, maybe go back to this slide for you to understand what I mean. So atomicity is really a single transaction and ignoring everybody else, just making sure that everything is executed or nothing. Then there's a second letter, that's C, consistency, Konsistenz in German. So a consistency condition is an invariant to the database. It sets a condition to on the database, and maybe let's enter the example. So for instance, assume for transfers within a bank, the sum over all account balances is always the same. So something like that. Yeah? So if you select the sum of all the money in the accounts table, that is the consistency condition. And you could use it, for instance, you could make sure before starting a transaction, you compute this value. Then after doing the money transfer, you compute the value again. And it must be the same value. Otherwise, you lost money or you created money out of nothing. It must be the same value. So you can use that as an invariant to check before the transaction starts and after the transaction wants to finish. Huh? And C basically means that a transaction T leaves the database in a consistent state when committing. So when a transaction says, I want to commit, yeah, the database can check those consistency conditions, and if the database finds out, no, come on, yeah, you want to commit, I understand you want to commit, that's fine, okay, cool, but you're violating this consistency condition. Yeah, then the database system will say, no man, no way, you're not allowed to commit, I will abort you, all of your changes will be undone. Yeah, so that's actually a very cool mechanism. It's a little bit like unit testing. Yeah? If you deploy code through GitLab, CI, CD, whatever, yeah, and one of the tests fails, you're not allowed to merge. Yeah? In GitLab, it's the same thing here. Basically, you say, yeah, consider a consistency condition like a unit test. Yeah? And so the transaction, the changes the condition goes through all of the testing. Yeah? And then if one of the tests fails, the database system will say, no, forget it, not you. Fix the stuff and then come back. We will talk again. Yeah? That is how this works. So important is, I mean, this is a kind of, unfortunately, often not so much used feature, but you should really use it more often because it helps you avoid problems from the get-go. Yeah, here is a couple of examples for consistency conditions we talked about. So primary key, for instance, that's a consistency condition saying that, hey, yeah, in that column or that collection of columns, the attribute values must be unique. Yeah, there mustn't be two tuples. There mustn't be more than one tuple having that specific attribute values. Yeah, that's this key concept we had already when talking about the relational model. Or you can say something like the foreign key must exist. So if you define a foreign key constraint, this attribute value, person ID, this foreign key references the ID in relation persons, this would say that whatever you try to insert into your relation, the attribute value of person ID must exist in the ID attribute, in the key attribute of person. Yeah, if not, you're not allowed to change it or insert it like that. That's a constraint you can check. Or stuff like that, unique, yeah? Maybe you want to make sure that first name and last name is unique and for whatever reason, and so forth and so forth. And so historically, databases developed many different mechanisms to handle this stuff. So one is called triggers and the other is called a rule system. So if you want to read about that, I added some pointers here. I just invite you and just tell you the takeaway message here is really if you are in a production environment where it is really important that your data is consistent, and if you know that the price of adding inconsistent data is high, then think about something like using triggers. It's a huge chapter on its own, but it's really a useful mechanism. When used with care, then it's really cool stuff, what databases can do at that point. Yeah, there are many more other consistency conditions. Those are just a couple of examples. Yeah? So consistency implies that you have to check the consistency conditions for each and every transaction. Yeah? So the database, and by that I really mean the set of relations and the data stored in those relations, not the system, not the database system, but the database, the stuff you store on the database system, must be protected against changes of transactions being applied to the database that violate any consistency condition. Yeah, so again, in other words, before a transaction is allowed to commit, the database system must ensure that the changes done by that transaction do not violate any of those consistency conditions. In other words, yeah, run all the tests. If any of the tests fails, not allowed to commit. Okay, with that we get to the third letter, and that is isolation. So concurrent transactions do not affect each other. For each transaction, Ti, it appears like Ti is the only transaction that is executed. What other transactions, Tj not equals I, do, or the effects on the database are not visible to Ti. Yeah, and if you go back to our Mensa analogy, I told you that, hey, you could actually do it like that. There's only one, at most one student at the time in Mensa. Yeah, what isolation actually means, you go to Mensa and for you it appears to be like you're the only student in Mensa, where in reality the Mensa is completely crowded and full, but you don't see that. Yeah? Maybe you get one of these new fancy Apple glasses or whatever headset, yeah, and wherever you look, yeah, like in this section, there's no student sitting here, there's no one is there, right? I mean, in Mensa, where's everyone? Maybe you also get headphones, yeah. Noise cancelling headphones, no one is talking. It's really alone, fantastic. I have this, that's the same approach here. So we get noise cancelling headphones and these Apple glasses, or whatever the name is, yeah, that is isolation. Yeah? We had Apple glasses here. These are the database Apple glasses and noise cancelling headphones. We invented that in the 70s already. Yeah? We didn't have Steve Jobs or Tim Cook to introduce this stuff, yeah? but it's the same level of coolness, I would say. Right. Yeah, and a sufficient condition for this is that the concurrent execution of two transactions transitions the database into a state that corresponds to one sequential execution of both transactions. What does that mean? So in the following weeks, I will be happy if something like that happens. So we execute T1 and T2 concurrently somehow. And as long as it holds that the state of relation R, after doing that concurrently, is the same as executing first T1 and then T2, yeah, serial execution, or first T2 and then T1. Yeah. So if whatever the state here, if that is equivalent to this state or that state, everything is fine. We are cool. All right, yeah? Nothing bad happened. Yeah? So that's an argument we will be using very often. In addition, the read operations of the transactions returning results must be the same to the sequential executions. Yeah? So that means that you shouldn't be reading stuff that shouldn't have existed. That we will look at that later on. Yeah? But maybe just remember this core argument. Yeah? We're arguing along the lines like, what if I had executed that serially? Yeah? Would I have ended up with the same state I'm in now? Oh yes, that's actually the case. Cool, I'm fine. Yeah? So the multi-threaded execution of transactions didn't ruin your database state. Okay, here's again the example that we had initially, mapping isolation to that. So however these money transfers are executed one after the other, in whatever order, first T1 or first T2, but in serial execution or concurrently, and concurrently meaning the individual read or write operations are somehow interleaved. The worldview of each transaction is, I'm the only transaction that's currently being executed. So from the point of view of the transaction, you don't see anything else going on in this system. That's what isolation is about. Come on. And that implies, of course, that we mustn't leave concurrently to chance. Yeah? So the database must be protected against concurrently executed transactions violating those properties I or C. We must protect the database from such changes, and that's what we will be focusing on the next 2 weeks. So basically on this I aspect of asset, that's what the lecture will be about. Yeah, there's the final letter, that is this durability, D. So what does that mean? If a transaction T commits, the effects of its write operations, i.e. the effects of the change operations applied by it, not the read operations, the W, the write operations, must be preserved in the database no matter what. So that means if you commit a transaction, you send this commit operation to the transaction, and to the database. You send this commit operation to the database, and then the database gives you an acknowledge. It says, yeah, I committed it. Yeah? Then you assume that the changes you did got stored on disk, got persisted, became durable, in other words. Now, the database system must make sure that it will never lose those changes, no matter what. Yeah? And if you think about that, there are a couple of things that can go wrong. Yeah? So what if there's a power failure? Now, what if the system didn't write it down to disk yet? Only it did the changes in main memory. Then it told you, yeah, I committed it, but it never wrote the changes from main memory to a persistent medium. What do? Yeah, or assume the database system said commit, then the data center burns down where the database system is installed. Yeah? So where are the changes now? Yeah? So actually, when I was at ETH, I heard a rumor about one of the banks in Zurich discussing, yeah, we should do replication. We should make sure that if we do a change there, we have a data center, and the data center should be in a distance such if a nuclear bomb hits this data center, we still have that data center. I mean, it's a rational thing to think about, but maybe if a nuclear bomb hits Zurich, you have other problems than syncing your data, right? Yeah, but that's the kind of things you have to discuss. Yes? I mean, think about Star Wars, Death Star, yeah? So if Darth Vader hits the Earth with a beam, yeah, no matter what replication you did on which continent, the durability cannot be guaranteed. Unless you replicated the data to a different planet or galaxy or solar system, then we're in business again. Yeah? So what that means is durability is, yeah, yeah, it's cool, but you never get it 100%. Yeah? There's always going to be a situation where you will lose the data. Yeah? But of course, you want to make sure that you, depending on the application you're developing and the requirements, that you can survive as many problematic situations as possible. And that's a whole lecture in itself in a way. So that's again something we will be looking at in the core lecture. So this implies we need to protect the database against errors of any kind. So algorithms and systems must be designed in such a way that durability is guaranteed in the event of errors of any kind. And yeah, that's a long story, but that's a feature you get for free with database systems, basically, to a certain degree. You still have to do things, but basic durability is there already. Yeah, with that we enter serializability theory. And we need to define what we mean by schedule or history. So in some books you will find a history. This term history, I find it pretty weird because it sounds like, yeah, something happened and we look at the history of events that happened. Yeah, but actually the argument I will be using in the lecture is, well, this is how we could execute those actions. And I will be calling that a schedule. Yeah, so let's see whether that is okay or not. Yeah, so it's not looking past, it's also looking in the future. And that's why I don't like this term history, but some books use this term. So we shouldn't be using that, we will be using this term schedule. So what is a schedule? That's a schedule as specifies for a set of transactions the order of their read, write, and commit or abort operations. So we write down a schedule as a strict partial order over the individual operations. And yeah, be aware that whatever is defined within a transaction, so if the transaction says, I first do a read on A and then I do a write on B, you mustn't change it within the transaction. And the operations have to be executed as a transaction specifies the execution inside. Huh? Yeah, let's jump at some examples for that. Before scoring doesn't work. Oh no, let's do the terminology. Maybe it's easier because then yeah. Okay, so in the following, we will also simplify the notation a bit. I will leave away this B, this begin transaction thing. I will assume that yeah, if the first operation being executed by transaction implicitly defines the begin. Yeah? So I'm not writing it down explicitly, makes it a bit more readable. That's what this notation is about. Yeah? So the opening bracket, if you want, I will be leaving away. Yeah, so with that we need the term conflict operation. So what conflict operation, two read and write operations. So here we define it as there's an operation OI, so it's an operation from transaction I on data object capital A. Here's an operation P from transaction J on data object B. And this O or P can be either a read or write operation. Yeah? So we have two operations. And now we want to understand whether that is a conflict operation. In other words, whether these two operations may cause a problem in concurrency. That's what we are reasoning about here. Yeah? And there are three conditions that all have to hold to make these two operations problematic or possibly problematic or at least a conflict operation. So these two operations are called a conflict operation if they belong to different transactions, which means I doesn't equal J. They both access the same data object, so A equals B, and at least one of them is a write operation. So again, both reading, no problem, but again, one of them is reading, that's a problem, possibly. So here are some examples. So assume we have these operations, two read operations here, transaction 1 reads A, transaction 2 reads A. That's okay, because it's only reading, no one is writing. Here, the transaction 1 is reading, transaction 1 is writing, no problem. That's within the same transaction, so it's not a conflict operation. Transaction 1 is reading A, transaction 2 is writing A. That's a conflict operation. All three conditions are fulfilled here, so that's a conflict operation. The same here, two write operations from different transactions on the same data object. That's a conflict operation. Here, another case where transaction 1 is writing object A, transaction 2 is writing object B. So this one here, this rule is not fulfilled. It's not the same data object, therefore it's not a conflict operation. No? That is the definition of conflict operations. Yeah, and then we can reason about how we specify those schedules. So one is to define a total order. Yeah? It looks as follows. So assume we have two transactions doing money transfers. Those are the two transactions. So this is again the €100 transfer from one account to another. So here, notice the B is missing, as here should be the B actually, but I leave it away to make it more readable. So we have this read-write on account 2 and read-write on account 7, and then there's a commit. Same stuff here, just this is a transaction from Bob. And now a schedule interleaves those operations from the different transactions. Yeah? Here also marked with color, so you see the blue stuff is from transaction 1, then there's an operation from transaction 2, then transaction 1 again, and so forth and so forth. So this is a schedule with total order, meaning I really define the total order of how the operations from the different participating transactions are executed. And what we will be looking at in the following is, yeah, okay, now I have this schedule. Yeah, and really read it as a proposal of the database system on how to execute those operations. Yeah, you can also look at it historically and say, yeah, that's how it executed it. Was it okay or not? Yeah, as explained before. But basically, we have to decide, is that a good idea to execute it like that? Will that create a problem? Will that create a consistent state that corresponds to any serial execution or not? Yeah, that's the argument we will be doing in the following. Okay. Yeah, an alternative to that is only to specify a partial order. So here, the idea is not to specify everything, to order everything, but just at least order each pair of conflict operations. Yeah, so here, for instance, you see that in this graph representation. Here you say, okay, those are conflict operations, obviously, so I make an arrow. I say this write operation from transaction 2 on object B is executed before this write operation from transaction 1 on object B. Yeah? And transitively, of course, you can infer that this is executed before that, because that is executed before that, which is executed before that, so which means this is executed before that. So actually, you could also write an arrow. Oops, you can write an arrow here, yeah? So it doesn't add more information. Transitively, you can deduct that arrow. Yeah? It's basically well, what's written here. Okay. Yeah, with that we get to conflict order. So now we have a couple of definitions. We need them, and then I will go back to showing more examples. So what's the conflict order of a schedule is a subset of that schedule that orders only the operations of the conflict operations. So basically, we here only look at the set, just the pairs of operations that are conflict operations, and only define an order for that. Yeah? So that's very similar to what we had before. So here you see it again. Okay, I write it down like this. I say, okay, whatever happens, whatever you do in executing these different operations, R2B must be executed before W1B is executed. And the same holds for these two operations. That's called the conflict order. Yeah, and with that we can play now with different orderings of those schedules. So first, let's look at a serial order. That's the most trivial or most obvious thing you can do. Yeah? Serial means if all transactions in S are executed, means that all transactions in S are executed completely one after the other. So here's an example. Yeah? You first execute all operations of transaction 1, and then you execute all of the operations of transaction 2. That is a serial schedule. Yeah? Transaction 1, 2, 3, 4, 5, or whatever order you wish, 4, 5, 6, 7. But there's no interleaving of the operations of the individual transactions. So that's a serial schedule. And of course, yeah, well, for n transactions, then there are n factorial possible serial schedules. Here's another example that's also serial. Here you first execute the actions of T2 and then of T1. Again, recall, I must not reorder within a transaction. That's not allowed. Yeah? The order is defined. The order of operations within a transaction must not be changed. Yeah? That's defined by the transaction. In contrast, this stuff down here is not serial because there's interleaving of these operations. Okay. So with that, we get to this term conflict equivalent. I alluded to that already because that basically makes now the argument whether a specific non-serial schedule is acceptable or not. So conflict equivalent means you have two schedules, S1 and S2, and they are called conflict equivalent if all operations of the conflict operations in S1 and S2 are specified in the same order. So in other words, you have a schedule and that specifies the conflict operations in a specific order for whatever reason. And now you look at another schedule and you again look at this conflict operations in that schedule. And if the order how these conflict operations are specified is the same, then these two schedules are conflict equivalent. Yeah? So you ignore everything but the conflict operations. Yeah? You only look at the conflict operations. Maybe that gets clearer when you look at some of the examples. So here's two schedules, S1 and S2. And if you look at the conflict operations here, those two are conflict operations, obviously. Different transactions, same data object. One is writing. So here, this write is specified before this read. Yeah? And if you now change these two, no, I'm not changing this to right now, that's the only difference. Yeah? Here from S1 to S2, the difference is that those two operations are swapped. That's the only difference in those in that schedule. Yeah? And but this swap from here to there doesn't swap the order of those conflict operations. Yes, it's still, this write operation is still executed before this is executed before this read operation, so I don't change that, and therefore this is equivalent. Yeah? Of course, you have to show that for each and every conflict operation to make sure that is correct. Yeah? Obviously, as this A and this B are different data objects, I cannot create an error by that, yeah? Because these two cannot be in conflict. Yeah? So it's fine that I change them. So, right, yeah, so that is conflict equivalent. And now we get to the main term we will be using, and that's called conflict serializable. So a schedule S is called conflict serializable if it is conflict equivalent to a serial schedule. Yeah. So before we look at two different, so conflict equivalent saying we have two arbitrary schedules, S1 and S2, and we say, okay, if the conflict operations are specified in the same order in both schedules, everything is fine. Now I'm using this definition to say, hey, one of these schedules is a serial schedule. Yeah, and the other schedule is a schedule I'm testing, it's an interleaved schedule. And that's basically how am I calling this definition? I'm invoking this function basically. So I'm saying, so I'm testing a schedule S, yeah? That is my S1 in the definition above, and S2 is a serial schedule. Yeah? So that's basically what I'm testing here. And what I want to find out is, to determine whether it's conflict serializable, is if it is conflict equivalent to a serial schedule. And you do that as follows. So if any schedule S can be transformed into a serial schedule by swapping non-conflict operations, S is conflict serializable. So how that works is basically, yeah, if that is a schedule here, this is your schedule S, and now you want to find out whether this schedule is good, whether it could be executed like that. In other words, whether it's conflict serializable, what you do is you start swapping the individual operations with the goal to find a serial schedule. It's a little bit like this Rubik's Cube. Yeah? All the colors are messed up. On each side you have all the different colors. You want to make sure that you have 6 faces of the dice, and each face has only one color. That's like the same thing I'm doing here. I'm swapping, I'm rotating these things to make sure that you end up with a serial schedule. So here I'm basically, what I'm doing is I'm swapping these two operations. Yeah? I can swap them because those two operations are not conflict operations. They are on different data objects, obviously, on B and A. Okay, cool, I can swap them. Now it looks like this. And then there's another rule saying that this commit you can basically swap with everything else. So C is not in conflict with any of those operations. So then I end up with something like that. Now I have a serial schedule. Yeah, first all the operations of T1 are executed, and then the operations of T2. So S could be transformed into a serial schedule by only swapping the non-conflict operations. This implies S is conflict serializable. Yeah? This is all the magic a database system has to do. So if there are concurrent transactions, there are these little men and women sitting in the database box and doing all of these swapping operations very quickly and determining whether, no, of course not. Yeah? There are better algorithms for that. Yeah? But the idea or the theoretical argument is very important. Yeah, and with that you can get to what we call a conflict graph or precedence graph. That's also, you will also run into that if you attend operating systems, I suppose. So that is an aggregated view of these schedules. So the conflict graph of a schedule S consists of the set of transactions participating in the schedule, T1 to Tn, those are the vertices, and one edge for each pair of transactions from S that have a pair of conflict operations. So basically this is an aggregated view of the schedule. So here I don't have, if you look at the graph structure here, I mean, where we have this partial order thing. Yes, I mean, this is a graph, right? So there's one node here, here's a node, a node, a node, a node, and then there are edges. So the nodes are the individual operations of the transactions. And then there are edges symbolizing those conflict operations. Now I'm changing the graph, I'm aggregating, I'm grouping it and saying, no, I create a second graph based on that, but now my nodes are the individual transactions. I will only have one node, one vertice for each of the transactions I ever find in such a schedule. So that's an aggregated view of the schedule. And that is the idea of this conflict graph or precedence graph. Yeah? So if you look at the example here, so if that is our schedule, we can directly infer the following conflict graph. Yeah? So just two bubbles because it's just two transactions, the blue transaction 1 and the red transaction 2. And yeah, there's an arrow because there is a conflict operation here being specified between these two. That's a conflict operation. So that makes it an error already. Right. So here are a couple of examples for that. Here, now I start omitting more things. I'm committing the, I'm not writing down the commits anymore because they don't make a difference for reasoning about those graphs. But here's an example. Assume you have a schedule with 3 transactions. Yeah? So blue, red, and green. That makes a graph with 3 bubbles, of course. And if you look at the conflict operations, you will do something like this. Yeah? So T3 has a conflict operation with T2, and so forth. T1 has a conflict operation with T2. If you look at the schedule T2, you see the only difference being that here another read operation is being inserted over S1. That's the only difference. You see that will trigger another error because in this schedule S2 there are now the conflict operations write to object B from transaction 2 and read of that same object from transaction 1. Yeah? So here's T1, here's T2, and I'm adding this extra edge here because there's a new conflict operation. And now the interesting thing is if you have this graph operation, we can reason about whether there's a cycle in the graph or not. So whether it's a directed acyclic graph or not. Yeah? So a cycle, of course, means that you have a path in that graph where you start from one node and end up with the same node. Yeah? So you can you can travel along the graph and end up with the same node you started in. That's called a cycle in that graph. So here's an example where there's no such cycle. Yeah? Whatever you do, if you start from T1, you end up in T2 or T3 and then T2. From T2, you can't leave T2, T3, you can only go to T2 and then it's over. But there's no cycle, you can't get back to the same starting node. In contrast here, you have a cycle from T2, yeah? When you start from T2, you end up in T2 again, or if you start from T1, you end up in T2 again and so forth. So you take this path. Yeah? You have cycles here in that graph. So that graph has cycles. And why is that interesting? Because you can prove that a schedule is conflict serializable if and only if the associated conflict graph is cycle-free. Yeah? And from that, so only if there's no cycles, it's conflict serializable. From this follows directly an important and practical algorithm to make a non-cycle free conflict graph conflict serializable. Because if you have a cycle in your graph, you can make it cycle-free by removing certain edges such that eventually no cycles exist anymore. Yeah? That's basically the algorithm you're doing. So it's a very famous algorithm that's also used in operating systems to prevent deadlocks. We will look at that in detail. Don't worry how that works next week. Yeah? But the core idea is that, and that is actually used in older database systems. Okay, so that's basically the theoretical backing we will be using to examine the algorithms that are used in a database system to make sure transactions are respecting isolation. Yeah? That's the backing. But before going into these algorithms, it's important to understand two paradigms in the world of transactions. And those paradigms are batch versus operation at a time. So when I show you those schedules, yeah, there's operations of certain transactions going on, doing stuff, yeah, like in this example. Maybe we go back to that example. Yeah, something like that. Yeah? So here's a schedule of these operations. And now what we're doing is we look at the schedule and do our reasoning. And that assumes that I know all of these operations all at once. Yeah? So I have all these transactions, they send me their operations, and now I have a batch of those operations and can do the reasoning about that. Yeah? All the actions, all the operations done by those transactions, all that information is available to the database system. So that's called batch reasoning or batch algorithm, because I know all of it and I can now optimize, I can make a decision on whether that is good or not. However, that is typically not how the database operates. How the database operates is called operation at a time. So that is the second thing. So a set of transactions sends operations to the database system in arbitrary order. Yeah, so a transaction is doing stuff, sending a command, an update command, another transaction is doing an update command, then one transaction commits, the other is still calculating, another transaction starts, then another transaction commits, is calculating, and so forth, and so forth, and so forth. Yeah? But for each of those actions, you have to make a decision whether that's okay or not. Yeah? In particular, at any time when any transaction commits, the database system has to make a decision. Will I allow that commit, yes or no? Yeah, that's completely different world to, yeah, you have all the actions from all my 100 transactions. I wait till all the actions, all the operations are in, and then I make a decision which of those transactions are fine and which are not. That's a completely different world. That's this batch world. Yeah? Yeah, in the operation at a time world, you have to make a decision for each committing transaction whether it is allowed to commit or not. Yeah? And this is called operation at a time. So most database systems are run in this mode. Yeah? Why? Why would you use operation at a time? If you think about the IMDb is not a good example, but whatever your banking system, right? Or a ticket system where you, I don't know, want to order a ticket. Yeah? Yeah, exactly. That goes in the right direction. Why would it be quicker? Under which circumstances? Yeah?
If there is not a lot of dependency there, right? If the requests are in conflict so much, then all of the sorting is overkill.
Right, very good point. Yeah, so that's excellent point. Yeah? So there will be workloads or transactions that create a lot of conflict. So if you have many transactions working on very few data items, many conflicts. But if you have those same amount of transactions working on completely separate data items, if you remember the initial motivational slides I showed to you, all of these customers of the bank working on different accounts, if they only put money on the bank and withdraw money from their accounts without doing transfers, there's no conflict. Everything is fine. Yeah? And for instance, for a ticket system, that could be the case. Yeah? I mean, okay, you have to be careful with if you have like whatever 500 tickets for concert XYZ, you have to be careful to not overbook, to not sell more tickets than they're available and stuff like hints, but like that. But that's not such a big potential for conflict. Yeah? So that's very important. But in more detail, so why operation at a time and not batching? You could still batch, right? What would that mean for the user interface if you batch and whether you do operation at a time? Yeah, you go on your, yeah, maybe someone else? And then you, okay.
I feel like on a really broad level, it would lead to a batch approach, would lead to a choppier experience because basically you can't get your data out. Once you're done with it, you have to wait until this whole batch is completed.
Exactly, yeah. Assume you go to a ticket system, yeah, and you say order. Yeah, that will be translated to a commit in the database system. And you expect that immediately you get a message, a window or whatever, an email popping up. Yeah, your order was either processed, it was successful or was not successful. Yeah, that's operation at a time. If you do it in a batch approach, batching means, well, all these transactions sending commits, yeah, they must wait till the database system decides, yeah, now as my batch is complete, now I will start processing the stuff. And once I'm done processing, I will signal back to those transactions, yeah, you can process and you can't process. Yeah, so you will introduce a lot of lag. It depends on how you define the batch, of course. If you say, okay, my batch means I wait for 2 seconds, who cares? Yeah? Like only after 2 seconds, whatever operations are assembled, I then make the reasoning. Yeah, you could do it like that, and then you won't ruin the user experience probably. Yeah? But if the batch says like, okay, I collect like whatever comes in from like half an hour, yeah, well then the user in the worst case has to wait like almost half an hour to get a reply. Yeah, so typically for web applications, you will do operation at a time. For banks, not sure what the current state of the art is, but at least a couple of years back, I heard that they will do batch operations often. So they collect all of the money transfers and then run it overnight. Maybe you get that when you do, with a German bank, at least you do a money transfer. It's not done instantly. It may take a day or something, and you never transfer money on weekends and only before 6 o'clock. Whatever, yeah? And then after 6 o'clock at night, I don't know, they run it, and then the next morning it's hopefully there. Yeah, so this sounds like batch operation to me. It makes stuff much easier, of course. Yeah? But for a highly reactive, interactive system, you want to do operation at a time. Yeah? And then you need different algorithms. Okay, this batching, just as a footnote, also plays a role in so-called blockchain systems. We did some stuff there. But it's basically, yeah. So blockchains were marketed a couple of years ago as a new next hot thing, but actually it's 95% database technology. And if you're interested, we wrote a paper on that. Okay. So we will need an algorithm that does this operation at a time thing. Yeah? It's because that's the assumption being made, and that's the default database systems assume. And there are numerous algorithms that actually do that. And in the following, so next week basically, we will look at two-phase locking and its variants, guaranteeing isolation. How do you use two-phase locking to guarantee isolation in ACID? Modern database systems typically use multi-version concurrency control. Think about, think of it like, it's a little bit like versioning, like GitLab, a little bit. Not quite how GitLab is doing it, but very related to. You version your data and then you do fancy things. You can also combine the two algorithms, but we will be focusing on these two-phase locking next week. Yeah, I really recommend you to be proficient with the material I presented this week. This always counts for the entire lecture, but this week it's really important you go back to the material, work your way through, because otherwise next week's lecture won't make any sense to you. Yeah? I really build upon this stuff, and I invite you to watch one of those videos. So that's an alternative explanation to transactions and assets, the one in German and one in English, but basically the same things. Again, explaining asset in more detail. Make sure you understand asset, and these videos might be suitable, or look at the Kemper or Emasri books. With that, let's call it a day. Thank you. See you next week.